Hello and welcome back. In the previous episode, we attempted to repair an HP A664A 3 GHz generator that we want to use as a backup transmitter in our Apollo comms setup. Our flea market instrument is currently unable to get through initial calibration without a long delay and several errors, and has heavily distorted output in the two lower bands below 375 MHz. Using the block diagrams and our noggin, we narrowed the fault down to two suspicious modules, the low frequency driver and the output amplifier. But to complicate matters, there is an interaction between the two due to the automatic gain control line that might skew our measurement of the LF driver. And the most suspicious part in the output amp is an HP proprietary Golden Box hybrid, which is unobtainium. So before we go any further, it is worth spending some time to fully exonerate our LF driver. If the fault is indeed confirmed in the output amp, then we should try to see if anything else outside the hybrid could cause it to fail, like a control circuit or a bias adjustment. Now, another thing that we wanted to try from looking at the diagram, it's very unclear how the automatic gain functions, but I think it is a DC voltage that comes out here. We could make triple sure that the driver is okay by bringing back its gain control to a reasonable level and see if it gives us an undistorted output. As a refresher, we can glean how the automatic gain control works by looking at the output amp block diagram. After we rectify the omission of this wire, which HP left out just to confuse us, it becomes clear that the amplified RF output comes straight out of the blue line, while another path implements an RF power detector with two diodes and some amplifiers, which should generate an automatic gain control signal proportional to the output power. This AGC signal is then steered towards three different outputs depending on the frequency band to be controlled. The path of interest here is the one coming out of J7. Now, taking another good look at the LF driver, we can confirm that the AGC signal is indeed coming into J3 and is applied to what looks like a mixer. But I think in this context, this symbol represents instead a voltage control attenuator, not an RF mixer. It attenuates the low band RF signal under the control of a DC signal. My thinking is that if I gave a proper DC input to J3, we might attenuate the signal enough to bring the LF driver back into range and get an undistorted signal. That would exonerate the LF driver and make the output amp the problem board. So what if I'm reading the tea leaves correctly? This is actually a DC level and its properties are too high or too low, and it's causing this to saturate, and that's why I have a bad looking waveform out of there. So I think the automatic gain control is J7 on the output that gets into J3 of the low frequency driver and regulates its output. So I think we can prove that our low frequency driver is working fine. So if I put back the AGC connection, it's overdriven, but if I just reduce the level of AGC, so I made a little cable here, put a little resistor, and so now through that, and here we go. We have a non-distorted signal because the AGC is at a lower level, the gain is lower. So it's exactly what we thought. Alright, it looks like our hunch was correct, and with the proper level of AGC, the LF driver is working correctly. So it is cleared of all charges and the output amp is the likely culprit. But what part inside this complicated board? If it is the amp in the golden RF hybrid box, we are somewhat hosed. But in the diagram, we can see that the golden hybrid is connected to bias and power circuits. Probably we should check these bits first, which should be outside of the golden box and made out of standard components. If the fault is there, then it may be repairable. And I was thinking before I try to unsolder the thing, see what's underneath, it might be just a bias problem or a supply problem in the outside. There is a low bias adjust here. Check if that would be the problem. That seems like a good bet for a distortion problem. And right away, I found an issue with this guy. I was trying to figure out where the pins of the LB bias, which is, I think, is the low band bias, go. And if I look at the resistance between the wiper and the ground, it's 0 ohm, so it's shorted there. The pot itself is 29K, and if I look at the pot, I think it's somewhat in the middle. Yeah, it's in the middle, so I shouldn't read 0 between that and the wiper. Do we have a simple bias fault because this guy's gone bad? I'm going to try that first. A little bit of desoldering of that little fellow here. Alright, so, well, false alarm is supposed to be grounded. If I put my flashlight at the back of the PCB, you can see this has a little cross, that's the connection to ground. This has a little cross, that's the connection to ground. And this one goes over here, goes over there, and it goes to the op amp, which I suppose does a little bit of analog math and translate this into whatever controls this. So I need to reverse engineer this portion now. But no, not the simple fault as we thought. I have traced the circuit and the DC bias circuit, and it seems to be an op amp that's connected to the golden module, and the pots control one of the levels. If that's the problem, then it would be this op amp that's bad, and I don't have it, so I want to try it in circuit, see if this op amp looks good, or we could try to adjust the bias. And if that doesn't work, then we are not going to be able to do very much more. Let's try to see what happens. It says calibrating down there. Okay, see you in 14 minutes. Okay, it's back from calibration. We got the same calibration error, and the bias does absolutely nothing. If I change the frequency, you can tell it's absolutely not regulated in amplitude. Oh, and now we have lost. There's only one band here. Oh, okay, I might not be correctly connected. Here we go. Do it like that. Alright. Oops. You went back to calibration. This was not plugged correctly. Okay, let's go for another round of 10-minute calibration. Well, fellows, as I was just turning the camera off, it let the magic smoke out. That little capacitor, a tantalum, didn't like being reconnected. Well, I think I know why it blew up. It's because my fault. It's because when I reseated the connector in, it didn't reseat properly. It was somewhere like this. And that probably did put 12 volts where it shouldn't have been. and probably the wrong polarity. So goodness, I hope I haven't done even more damage to the poor output board here. Oh no, I broke it even more, and for once I won't curse at the tantalum because it apparently gave up its life to save the circuit. What happened is that when I hooked the output amp back in the instrument, I did not insert the power connector properly. That connector is a DB15 female connector. Normally, the male connector on the board side has a keystone-shaped metal shroud that prevents any wrong insertion, and therefore DB connectors are very sturdy and safe. They are actually of military origin. But somehow on the board receptacle end, that lip had been removed, I imagine either from factory or from a previous repair, as that connector had been previously replaced. And I didn't realize that, so when I plugged the connector back in, nothing prevented it to go in the wrong position. It went one row down from where it should have been. As far as I can tell, that resulted in sending minus 15 volts into the plus 5 volt rail that powers the control logic. Then the tantalum cap objected to being reverse biased and it blew up, protecting the rest of the circuits from a longer exposure to minus 15 volts. Thank you, tantalum cap. However, some things don't work anymore, so some of the 5 volt chips didn't like it. We now have to figure out which ones, which is going to be difficult without the schematics. Yeah, just what we needed. Alright, we soldered another capacitor right here. And it powered back up. Good news, it still works on the higher frequency, 500 meg, no problem. And then we get back the old fault at 300 and something megahertz. There you go. Now it goes crazy as it did before, but we have broken it a little bit more. There's now a unlevel light that wasn't there before, and it looks like we have lost the 175 and below megahertz range. So if I go over here, punk. Yeah, 180, I can't remember where the cutoff is. So unfortunately, I think I have zapped a few things in there because I lost the lower band, 187.5 megahertz and below, which gets generated as this down converter. And I don't think I zapped the down converter, I think I zapped some of the logic that controls it. So it's getting more difficult. So what do you do when you have unknown instruments that don't work? You get another one that doesn't work. And Philip, you have another one of these.
Yep.
But yours has a different fault.
Mine has a different fault that hides at times. So
right.
Intermittent. As I go up, 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 bang. Very sad.
It has a much more annoying fault than mine. I first spent some time diagnosing Philip's instrument. Long story short, the fault is at the bottom of all bands and has to do with a malfunction of the Yig oscillator or the PLL loop when the Yig is close to its 3 GHz lower end. That would be way harder to repair than ours without spending considerable time on it. Fortunately, Philips owns a second working unit, so repairing his is not the main point. The output amp board in Philips' instrument appears good, so I want to use it to do some A-B comparison with mine. It should help me figure out what I have broken and also give me some solid comparison points on the bias circuitry, which I was debugging before the mishap. Yeah, it goes bad. We correlated all the spots where it was bad, where the Yig oscillator was at the bottom at 3 GHz. Here we go. It tells us that the problem is in the frequency synthesizer, something that's not documented, super complicated, in a loop. Our chances of repairing this one without spending inordinate amount of time are very low. So it's in the frequency generation, but the amplifier seems to be working fine.
Yeah, so we can use it to help debug yours.
So thank you, Philip, and thanks to all the good Samaritans and patrons that contacted me after the first video to lend me their units or extra boards. It's awesome to get that kind of support from the viewership. Anyhow, it appears that I have now lost the lowest band, 0.1 to 187.5 MHz. We know from the first episode that it is generated in the down converter by subtracting a constant 1 gig from 1 to 1.1875 gig in a mixer. I don't think I zapped the RF down converter itself, which is powered by plus minus 15 volts. It is more likely that I zapped the control lines coming from the 5 volt section. There are only two, one of the AGC lines that we previously discussed and what appears to be an on-off control line. Both are now lifeless in my instrument. By the way, the down converter components are easily found on the board. The three RF amplifiers are under the round heat sinks. The mixer is nicely labeled. The AGC control line is marked MOD and the on-off line is marked SW, both coming via feed-throughs from the control section. You can even see the beautiful low-pass filter that gets rid of the sum frequency component. And if you squint, you can see the voltage control attenuator that's connected to the AGC line and is implemented with 3-pin diodes placed in the 1 GHz input strip line. This I have zapped, but I don't think I zapped the actual amplifier. It's a very simple board. It's 3 amps, 1, 2, 1 here, and a mixer. And those should be powered by 15 volts, and they should have resisted the over voltage problem. So it's here. It's turned on and off by those signals out there, which are DC, and I think this is what I zapped from the logic section. So let's measure those. Alright, so I have hooked up Philips instrument and I'm looking at the control signal, which I think is dead, and on mine. And mine is always at minus 15. And I'm going to go to lower frequency. Oh, that's where yours fails in a different way. It's up. So mine doesn't show that. My level never goes to 1.75. So now it has gone into AGC regulation. And I never get that signal out. So I have lost the AGC control, I guess, on mine. And then the other one that I think I've lost both signal because I saw no activity on that one. That is the one that mutes the amplifier. I put it on 187, 1, 2, 3, 4. Should still be 0. No, it went up. There you go. Donk. So this one activates too. So I know what those signals should be.
So you have to reverse engineer where those signals come from.
Yeah. So we now have confirmation that my control signals are dead and know approximately what this should be. We need to figure out how they are generated on the board so I can debug it. Okay, so I've made some progress in reverse engineering my board here, and I've been helped by some schematics that are not from the same instrument but are from a similar instrument. So yes, of course, the schematics do exist. They are called the clips for Component Level Information Packet Set. The clips were separated from the service manual by evil Omnicord HP and are surmised that only the service centers had access to them. But one of them has escaped into the wild. Unfortunately, it is not for my instrument, it's for the HP 8643, part of the same family but a different RF instrument altogether. Somehow, Artec Manual got their greasy hands on it and scanned it. It is available for a few bucks. And although the RF and analog parts are completely different, there is a logic section that keeps reappearing on many boards. Look at the left side of these schematics. It implements the digital communication with a processor. Looking at the chips, it looks like I have a version of that block on my board also. If that's the case, that would be immensely helpful. And it's a totally different instrument on the RF perspective, but I see the boards, the control of it seems to be similar. And you can see that they made their own serial protocol. You have clock, data, strobe. They go into a shift register, and then it goes into a series of latches. And I find this collection of chips on my board. They are over there. This is all those chips, and every time you see one of those chips here, one of those big chips, this is a latch, which means it will have 8 bits for whatever chips it controls. Let's look at this logic block schematic. It implements an I/O expander using a simple serial protocol. There are 3 input lines coming from the processor: clock, data, and strobe. Each line is then buffered by a Schmitt trigger. Let's follow the data line. It goes to this chip, which is a shift register. A shift register is a basic serial to parallel converter. It clocks bits in one by one, after which the bits march on every clock cycle and become progressively available on 8 outputs in parallel. Quite predictably, the clock input signal controls the shift register, so I imagine there is a clock pulse accompanying each data bit. A nice thing with shift registers is that you can chain them and make them decode arbitrarily long serial streams. And that's exactly what they have done here. Bit 7 of the first shift register is chained to another shift register, also controlled by the same clock. These two combined registers can decode a 15-bit word. After 15 bits are clocked in, the first 8 bits should appear at the output of the second shift register, here in pink. These 8 bits are then forwarded to 5 identical chips. These are the 8-bit latches that I was just referring to. But these chips won't do anything until they are selected. The selection lines in blue here are in turn connected to the first 5 bits of the other shift register. Let's suppose there is only one selected. This chip still won't do anything until it receives a strobe input. Sure enough, the strobe line is connected to every latch by the dark blue wire. For now, we only need to be concerned about this strobe line, as the other chips are not selected and won't respond. I imagine that the way this works, the processor outputs the 8 bits of data, the 6 bits of latch address, and when all is done, sends a strobe pulse. At this point, the selected chip will latch the data available on its inputs, memorize it, and make it available on its outputs, here in purple. Each of those output lines then connects on the board to whatever analog function it controls. It's a simple way to implement a digital control of many lines on a board. Now that I know all this, all I need to do is find which latch my 2-bit down converter control lines are connected to, and follow the whole chain to see where I lose it. So armed with that, I was able to untangle the whole path of the command signals, and I reverse engineer enough to find out what controls my RF section, which I have killed. It's this analog switch controlled by this latch. And so somehow it does, this analog switch is not toggling, so I'm losing the signal over that series of TTL chip. So let's see if we can find if they are all dead, or if I only killed one, or if we can revive that at least. And right now I'm hooked up at the input with the clock, data, and strobe. See if I reverse engineer them correctly. I think I did. I can see it right there. So you have the clock, you have data, and at the end of the word you have the strobe. So the board is receiving the signal correctly, and we should be able to trace them around and see where we lose it. So far I checked that I have all my input serial signals, and then the first thing they do is go through a Schmitt trigger, after which they go through 2 shift registers, and the data bits of the shift register are connected to these latches here. There's 2 over here, and there is 1 over here. And this is the one that controls the part of my car that's not receiving its control signals. So we know we have all the input. Let's see if we have all the outputs. So I am now on the output of the Schmitt triggers. The signals are right there, so that works. First chip, good. Well, that's mighty good news. I was afraid I zapped all the TTL chips, but we get all the outputs out of the Schmitt trigger, so the first IC is still good. Let's move on to the next chip, which should be the first shift register. I've moved to the next chip here, which is this shift register. Yeah, I have data. Okay. So I haven't broken the shift register. Next shift register. Yeah, we have data. It works too. Okay, so that still works. Well, looks like we haven't broken the first nor the second shift register either. Let's see if we get some activity on the data input to the latches when we change bands by monitoring some of the pink lines here. We are now on to the latches. Right, we want to go over here. So I'm on the latch and it's now calibrating and there's lots of activity in there. And so I should get my switch at 187.5 megahertz. Yeah, it did. It tried to do something. So I have something at the input of my latches, but I haven't checked the output. We're still good up to here, so let's see if we get something on the other side of the latch on the output wires here. I'm surprised so far, but I can guarantee it's going to get bad at some point. The output to latch controls this analog switch, and this analog switch controls the two signals that should turn in on and off my down converter here. What I want to see is that this input gets toggled, and if it does, then it's the analog switch that got zapped, which is good because I have one of those in my bins of old circuits. So we're watching for the green to go up and down as I cross the band. So here I'm above band, still above band. I'm going to go below band. Yeah, it does. So, and I go in the other one. All right, so this whole portion works. So it works up to here. I'm getting that signal toggling. And I'm not seeing this toggling. So it would tell me that my analog switch is the chip that got zapped. But that would mean that this guy is the bad one. Well, wouldn't you know it, the whole control chain checks out good until the purple output of the latches, after which the signals go to work and interact with analog stuff. The board uses several of these analog devices 201A quad switches to interface between the latches control lines and the analog hardware. Think of these as electrically activated switches. It's a very handy chip, 4 TTL inputs to toggle 4 analog switches. So I made myself a little analog switch chip tester. 4 switches. They all work, and this is the one I just took from the instrument. Okay. Ooh. Very bad chip. 2 that are stuck on and 1 that is stuck off. So definitely a dead chip. Alright. We found a fault. So let me desolder others because I have a feeling they all got zapped. Oh, and it's hot on top of that. It really doesn't like it. Another one. Freshly desoldered. No? This was plenty fine, thank you very much. And here's the third one. And that one's a good one. So just one that was bad. Okay, good to know. So I've replaced my single bad chip, put the other ones back where they were, and we'll see if we have, at least we were back to where we were before we zapped it. We're not, because this is red and it wasn't red before. Okay, we need to wait About 10 minutes until it calibrates.
A little longer than a few minutes later.
Alright, some good news, we have recovered partially. Now if I go to the lower band, I have signal output. So we're somehow back into where we were before I zapped it. Well, that's a bit of an overstatement. I have recovered the down converter and the lower band of the instrument, which is a big relief. However, it still has the original fault of being distorted, plus a brand new one, this pesky unlocked red LED that wasn't there before our debugging incident. But we are crawling out of the hole we created for ourselves and are slowly but surely gaining more understanding of how the board works. It feels less daunting now, which makes me more hopeful about the next phase of our debugging effort. See you in the next episode!